Hope everybody enjoyed the 2 chapters, but the heavy reading in chapter 8. As always, this hasn't actually really changed too much, except down here. Now the exam, the 8th week would have landed on Easter, and after having already brought you all out on Super Bowl Sunday and Valentine's Day, I figured I couldn't do a third holiday, so there will be a break. There won't be any classes during the Easter holiday, but the exam will be the first week of April.
So you get an extra week to study.
Exactly, yeah. So don't take that week off. By all means, study as hard as you can. But
get 100 rather than 99.
Exactly, yeah. The other thing as well, we have the exam proctor. He's locked down. He's ready to go. So he'll be out here to test all you guys and hopefully get you guys a call sign and ready to get on the air. So, but that's still a couple weeks away. Yeah, so that was about the exam.
Couple weeks.
Sorry?
5 weeks, 4 weeks, I guess, eh?
4 weeks, yeah.
Yeah.
Oh, we'll be surprised how.
I got more studying to do yet.
Excellent. Any questions?
And it's a multiple choice, right?
Yeah, so multiple choice, 100 questions. The breakdown is available on the website from Industry Canada. There's like 25 law, 25 basic electronics. It breaks out the number of questions in each. But
how many in logarithms?
1 or 2.
Not to psych us out, but suppose we come out with, instead of 98, 58. What are the rewrite provisions?
Up to the examiner. He will, if he has the time. Probably not in this situation, because I think he's coming from Peterborough.
Yes, yeah.
But you can do it right the next day.
Oh, okay.
Sometimes you write again and going to do it again.
Oh, okay.
You know,
Yeah. So.
There's no minimum or
Okay.
wait cooling off period.
Yeah, no. So they're not going to make you wait a month or anything like that.
Okay.
So.
You might need a month to study more.
To get 2 more marks, right?
Well, not that anybody's going to fail, but I
Exactly.
mean, you know what? Even if you say you don't get 80 and you want to get 80, just stick with the books for a few more weeks. And there's enough examiners in Durham. You know, if you can't find them, we'll hook you up with somebody.
Yeah.
And do it again. You'll get it.
And that was going to be the next question. Actually, suppose you came in just below and you wanted to increase. You already had a pass, but you wanted to get a higher pass in honors.
Yeah. Some examiners will charge a minimal fee. I don't know what they are. It's up to them.
Yeah.
They can charge up to so much, and it's just a matter of, like I say, the guy coming from Peterborough, so we're not sure that night if he would do a rewrite. But I know there's a couple in the Whitby clubs. There's the one in the Pickering club. So just a matter of getting whenever you're ready.
Okay.
And do it. And
Alrighty.
and do it right away. Don't.
Yeah.
If you're thinking of rewriting, don't put it off.
Yeah.
Just keep studying and do it again. Because if you wait a month or two, then all of a sudden now you're trying to relearn stuff.
Yeah.
So when the test happens, we have upstairs, we have the dining room and the kitchen, so we can accommodate 8 people for the testing. So are you opening it to any club members who didn't take the class that actually can slip in and take the test?
So for the test, we'll talk to the examiner, see what his exam fee is. But anybody who's paid the $50 for the full course can get it. Anybody who hasn't will have to arrange privately with him. So.
I guess the thing we'll have to arrange, Alex, is just while we're on the subject, is confirm how many we have in the course, and I guess at the next meeting we could ask if there's anybody who's going to write, and so we know, because I guess he has to bring the number of exams. I don't think he'll want to print them out here. He'll probably print them out before he comes and bring them with him. So
Yeah, all I'm saying is if there's extra people, we can probably set something up.
it'd be nice to know.
As long as there's a proctor watching them, that's
hopefully we'll know not the Easter weekend, the weekend before that, we'll have a pretty good idea who's writing. I would hope anyway.
Yeah, well, I've already got the list of everyone who's paid for the course so far, so that week we'll make sure that everybody finally gets taken care of.
And you know, even if you don't think you're up to it, right?
Yeah.
You might surprise yourself.
So.
You know, a lot of it's memory work, eh?
You know, you get the right question, you'll know that question. Like you know how you've seen the questions, 2 or 3 questions around the same subject, same answer, and you might get the one you remember. So you know, if you're feeling a little right, it's not costing you anymore.
Yeah.
No. You gotta give. You know.
I've been purposely avoiding doing any of the questions so that not to psych myself out. But finally, the other night I went into the book page and I did one of the chapters, or actually a chapter and a half, because I decided to quit while I was ahead. And I started on chapter 1. They were pretty easy, and I got them all right. And I thought, I'm quitting. but it is a way of doing it. You know, like,
That was basic. That was the basic review?
Yeah, I started aiming low right riding Shetlands.
Fun. Alrighty, so I guess we'll just roll on in. As we did phonetics, so this week we're going to practice Q codes again, and then next week phonetics and Q codes. So I guess the way we're going to go is we'll just go around the room. Each of them will pop up. I've specifically only chosen the cue codes that are on the exam. This isn't the entire set, but we're going to go around the room. If you don't know, you can ask out for help. Try not to shout out answers though, so the person has as long as they feel they need. So, and if you really want to, you can open up to the section just so you can peer in case you're running out. All right, we'll start it off. All right, QRS. So that would be receive strong. So
Say more slowly?
yeah, yeah.
Receive slow.
Receive slow. Yep. Send more slowly. Okay. We'll pass it along, I guess, to Steve.
What's your
QTH.
location?
Longitude.
What's your location?
My location. What is your location?
Yeah. mhm.
Yep. All right, next one. Every time you see
Was
this
that
one.
Morse code? You is that what you're
Use it
asking?
all the time, I can't think of this one.
So. No idea.
K? Is that in Q right? No.
QK?
Nope.
No,
QRL.
QRL?
Oh, wait.
Is that the answer we're going with, I guess?
Is it?
Survey says QRL.
You
Perfect.
know, the funny thing is that a lot of guys use QRZ, which is this frequency in use.
Yeah.
And they'll say that, and it's not. It's supposed to be QRL. I don't know how
Yeah,
many
you're-
times you hear QRZ. It's a
Could you
frequency
flip
in use.
that back from the...
How about flipping it back one more?
What is the proper Q signal to see if the frequency is in, okay.
So QRL means if you're busy.
Yeah, I
right?
was
Or if the
thinking
frequency is busy.
Yeah,
or-
receive lots is your.
Yeah, receive
book,
lots.
it's busy.
Exactly.
Yeah.
So.
Did you get that,
Before
Bob?
anybody starts, you hear QRL
Bob, did you have the right
and a question
answer?
mark. Okay? QRL and a question mark, it does nothing, it doesn't hear anything back, then you hear it calling CQ.
Yeah.
Oh, okay.
So. Alrighty. Yeah. QRL question mark. So I guess it's a question. Okay.
Oh, okay.
QRN means. I guess we can either pass it. I guess we'll skip Bob because we got lots and lots and lots of experience. So hopefully he knows. Sabrina.
Static electricity, or you're bothered by static?
Static, yeah.
Yeah.
So, I'm trouble by static. Perfect. I'll pass along now to Tom, I guess.
What other station sends QRS?
QRS.
Yes.
We get. Yep. So. All right. Next up. I guess we'll pass it on over to Jeffrey.
No, no. These are bad.
Who's calling me? Don't know by which Q signal.
The QRI?
QRI? Mm,
No.
no.
Tony.
Donated by the signal.
These I don't really know.
Okay.
These I've had trouble with.
That's fine.
Because they
So
don't seem to make any sense, a lot of them.
there.
Is that
Yeah.
QRA?
Nope. So it's actually
Yeah.
QRZ.
Yeah.
QRZ.
QRZ?
Yeah.
I got that.
Who are you? What is, who's calling me?
QRZ.
Twice.
Oh, yeah. So, yeah. Who was calling you?
Yep. Alrighty. Next up we have the Q signal, which signifies "I will call you again." Is. Guess we'll pass that on to Glenn, if you want.
That's the one I remember.
Do you remember that one?
Yeah, that's
Right
the
here.
one I do remember.
QRX.
Yeah.
QRS?
X.
X. No, I
Yeah.
didn't think it was S. Okay, QRX.
Yeah, that's the exchange. QRX. All right.
Okay.
Over to Shay. We have.
Oh, no.
Okay. I guess we're on to the questions. So.
That was all of them.
Okay.
You two scooted out quite nice and luckily at the end there. So, all right. So those are the only Q codes that are on the test. So don't panic too much if you don't have them fully memorized, but keep on at it. I guess that's the best I can say. I just keep studying. So, on to the questions for this evening. The first one is a fly. A mismatched antenna or transmitter may or transmission line, may present an incorrect load to the transmitter. The result may be.
Number 3.
It can actually be all four. If everything blows in order.
As each of them fail. Yeah, okay.
Yeah, number 3, I guess. Eh?
Number 3? Alright. Survey says, yep, number 3. So yeah, impedance mismatch reflects power back into your transmitter instead of the antenna. But as Bob said, if your transmitter starts to go, then the drivers will go, and front end, and then the mic and everything.
Modulation's gone.
Exactly.
I have a question.
Yep.
That's the one word on this study course that's really troubling me.
Impedance?
Yeah, because it's used everywhere. And
Okay.
to simplify it for a bonehead, in layman's terms, what actually is it?
So impedance is a partial reflection. So markers, because we'll do some doodling now. Oh. So sorry.
Move every week.
Okay. There's a really fantastic video, I guess I can point you at first. It's one of the older films on the site under waves. It's the one with the wave generator, the mechanical wave one. That's one of the places he'll talk about impedance. Essentially, the problem is if you have two dissimilar resistances to current. Yeah. So, all right. So we'll pretend. Now we get to play which marker is the right
That
one.
one maybe?
All right.
Wait.
Okay. So, yeah, that's a good marker. So let's say we've got the output of our particular system, all right? And just as a diagram, this isn't exactly the way it works, but let's assume that our antenna sort of does this, okay? Now, the reason we're going to do this is because we have to talk about what impedance is actually doing to our signal, and we're talking about electrons, which are particles we can't see doing things that are similar to mechanical systems but aren't. But in this sort of system, you can imagine that there is a sort of wave, all right? And it's traveling out of your particular system, right, your transceiver, and it has to enter into the actual transmission line. You have a problem right here, though, right? And this is because the signal doesn't actually fully get into the line. Some of it is going to bounce back, right? So if we draw this diagram again, as the wave is trying to enter into the transmission line, some of it gets reflected back into the system, and only some of it is actually able to enter the transmission line. So in order to fix this, we need to use a device that essentially allows more of the energy to be gradually added to the system as opposed to abruptly, right? You can imagine this sort of as slanted walls that allow this sort of wave to kind of get smaller and smaller as it needs to fit in that passage. This is a very simplified, inaccurate version of what's happening, but mostly because all we know what actually happens is based on equations, not based on observation, because we can't really see electrons that well.
So in actual terms, it's rebounding.
Exactly, right? It's rebounding. It's more of the technical term would be reflection.
Reflection, yeah.
That there's a partial reflection at the junction point. And that's due to the fact that they have different resistances between the two different parts. So, Steve or Bob, if you guys have any better analogies or comments?
No, I just want to say that what you're showing there is actually what took place in that little box I had here last week, that antenna matching box that had two capacitors and an inductor inside.
Yeah, so that would have taken care of this, right?
What does that?
Yeah, I mean, impedance is you have a load. Your speakers, you got 8 ohm speakers, 4 ohm speakers, right? If you use the wrong impedance, you're not getting all the sound or proper sound out of your speakers. In a simplified version, it's exactly this. You have to match your load to your antenna to get the most out of your radio.
Well, that was my next question. Yeah, you have to. I was on to section 7, I think, about Coax.
Mm-hmm.
You have to match the impedance.
Yes. Yeah.
How is that? Is there any relevance?
So the impedance is a mathematical number that greatly simplifies some of the calculus involved in determining what goes on. So essentially, the impedance allows them to pre-calculate a particular property that something has, like a transmission line or an antenna, and they can assign it a value. So an antenna might have an impedance of, say, 50, right? The 50 ohm impedance means that if you try to match it with something of, let's say, a lower ohmage, right? You match it with let's say your antenna is a 300 ohm antenna, and you only have a 50 ohm transmission line. The amount of power reflection is going to be about 6 to 1 from that particular antenna into the transmission line. I may have that a little backwards. Yeah. So the problem is essentially, because you're going to be transmitting so much power through the transmission line and then into the antenna, that junction, they have different resistances to that wave, right? And that's a function of...
Well, you would cure that with one of these.
A balun, yeah.
Antenna. There's a balun here.
Yeah.
The coax goes on here, the antenna's on here, there's a balanced line here, unbalanced line here, and this would be a 6 to 1 transformer in here. So
Yeah,
that
it's in the book, isn't it?
transmission line
Yeah.
would match the antenna at that point.
You can buy them 4 to 1, 6 to 1, 9 to 1, depending on what antenna you're using, and
Yeah.
All right, eh?
So,
Now, does a rebound happen if it's, I suppose the source was the opposite, so you're going from the little to the big?
So, yeah, it does do it in the opposite way. Again, this is why the oversimplified model doesn't fully work. But if you do have, let's say if you had, yeah. Again, this sort of drawing doesn't fully capture the system, but it does do the exact same thing in the opposite
Yeah,
direction.
rebounds, yeah.
Exactly. You have to make a more gradual
Transformer
change.
works both ways.
Yeah.
Yeah, there we go. So, all right. Any other questions on impedance? We'll have more questions on it as we slowly introduce the concept through the night. But, alrighty, moving on. All right, what connects your transceiver to your antenna?
Well, you could use two of them there, but
Second one.
yeah.
Second one. All right, and the answer is perfect. Yeah, transmission line. So,
But you have to have a ground wire.
well, not
That's a
really.
good question.
No?
Where does the ground wire go?
So ground wire typically would go from the transceiver to the ground, which would ground the outside section of your transmission line, the copper braid.
So when you're grounding for lightning or whatever,
Okay, so if you're grounding for lightning, then you would have
antenna
to.
in here gets hit by lightning, right?
What a question. There's an RF ground, there's a lightning ground,
Yeah.
there's an AC safety ground.
Okay.
They're three different things, but they should all be
You know what
tied
the AC
together.
safety ground is?
They
And
all-
lightning
yeah.
ground grounds the whole chassis assembly.
Yeah, and they all have to be tied together, and if they're in different spots, when lightning strikes, the entire system has to go up and down at the same time. Not
Okay.
one higher with respect to the other, so you get a voltage across them to blow out your unit. They all go up and down, so nothing gets hurt.
So you come back to the transceiver
But
again.
you're usually talking about the RF ground at this point, and it depends on the kind of antenna you've got here.
Oh yeah,
Okay?
forgot. All right.
Yeah, well, you're teaching us, right?
No. By all means,
I was
please. You've
looking
got.
at- I was looking at the book and it says about ground, but it doesn't say where you put them.
Yeah, I'll go through it.
Well, moving forward with ground, in the construction, doing line maintenance as a power lineman, we were taught to take an 8-foot ground rod and hammer it into the ground on a 45-degree angle. Could we use something in that capacity for grounding a trans receiver? Yeah, we could do that.
Yeah, well,
They
it doesn't make a good RF ground,
No.
but
No.
it does work. It's
Yeah.
not perfect.
If you're grounding like for lightning protections or static electricity in the air per se,
Yeah.
and running it to ground, it'll work.
Yeah.
RF grounds are really complicated.
Yeah, they're extremely
Because
complicated.
you get into ground loops in your radio, and if you don't ground it properly, and
You ground it at one point, not in 2 points.
then you got RF bouncing all over the place in
Yeah.
your shack.
So
The simple
For a
answer.
radio ground, it'll work for you.
Yeah.
For the transmitter, for a receiver, but for the transmitter ground, it's a different story.
Yeah.
It's gotta be more efficient. But, for instance, I have to use that at field day because, I wanna keep the, spark of the generator out of my receiver. So I have to ground everything to the actual earth,
yeah,
the
okay.
generator and the receiver.
So is there a natured question on this? Is there a correlation between this and the exam?
There will be, yes. So when they're saying that ground gets pretty complicated, it goes into a lot more detail on specifically calculating ground equations in the advanced exam. Unfortunately, in the purposes of the basic, they try to be like, and magic, and there's a ground, and you don't need to worry about it too much.
Oh, good.
Yeah. Yeah. So for the most part, you just need to know that there is a ground, things have to be grounded, and which things should be grounded, but it's not going to ask you which things shouldn't be grounded, for example. So when it refers to a ground, it's typically talking about balanced versus unbalanced. Balanced being that it's balanced reference to each other, and unbalanced is that it's balanced reference to ground. So,
That's exactly right.
yeah. But
Anything in the earth itself,
that's typically what they're referring to
Yeah,
with
as
some
opposed
grounds.
to the other kinds of grounds.
Typically, yeah. Well, it's more AC ground, right?
If you're gonna talk about AC ground
That comes
and
from
lightning
the main
ground,
panel.
that's, AC ground and lightning ground have to be in the earth. But a ground for an antenna can actually be raised up on the roof, because those are the radios you'll see on CB antennas.
I was wondering about that.
They're around it, yeah.
Yeah. So, unfortunately, they call like 9 things the same term. Well, it's not 9, but yeah. Like they really should come up with better names than ground for everything.
That's good. This is good. I like that.
So
Yeah.
this is kind of the fun joke I had. So the microphone's connected to the transceiver's connected to the transmission line, the transmission line's connected to the feed point, the feed point's connected to the dipole. But that's the basic structure right for right now. Later, we're going to have to actually know what the transceiver is made up of and what connects the microphone to the output. But for now, that'll work. So, alrighty, the characteristic impedance of a transmission line is determined by the physical dimension or relative position of the conductors.
Yeah.
And we get, yep, there we go. So, oh, there is no, oh, I guess I forgot to write a description for that one. Not really much else to say. Yes, that is what relates the two together. So your transmission line, see, the length of the line doesn't change the characteristic impedance. No, it should, shouldn't it? No, okay.
The next question answers that.
Oh. Characteristic, oh, okay, yeah, sorry. So yeah, the characteristic impedance of a 20-meter piece of transmission line is 52 ohms. If 10 meters were cut off, that is, it's cut in half, what would the impedance be?
We all know that.
52 ohms.
52 ohms. So,
Stays the same.
yeah, it stays the same. All right. I was thinking antennas. That's the other problem you're going to run into. Impedance of transmission lines has different properties than impedance of antennas.
But you're cut it in half, how can it be the same?
Because impedance is measured based on the actual line itself, the type of cable you're using.
Oh,
Whereas,
nothing to do with the length.
and nothing to do with the length.
Oh,
That's
absolutely.
antennas that have to do with the length and their impedance.
Your RG58 is 50 ohms. The RG75, your cable, or RG6 for your cable, is 75 ohms. Your cable TV is 75 ohms. The RG59 is 75 ohms. Off the spool, 10 feet, 75 ohms, 1,000 feet, 75 ohms. The characteristic impedance of that cable, due to the this thing, the size and conductors, yeah,
The word is the characteristics.
yeah, of that line.
Yes, yeah, okay. Mhm.
So, all right. Antenna impedance relates to the voltage and the current at the input of the antenna, not the length. At the transmission line, not the antenna. Yeah, all right. The characteristic impedance of a coax line Two. Yeah, go for it. Yep. Yeah, so it can, so it may be, but it doesn't always have to be. So, it's because the particular line has a particular impedance set when it's manufactured. Well, not set, but when you buy it, it has a particular impedance. And changing those around can make it different values, but it doesn't have to. So.
I got that wrong when I was answering you.
We just think of RG58, it's 50 ohms, RG8, the big stuff, or RG213, and LMR 400 are all 50 ohms.
All
Big
different-
stuff.
All different sizes,
Yeah,
That's a
but they go different sizes. But,
different handle.
like he says, it can change it too. So.
The big wire can handle bigger. More.
Look at RG6 is 75 ohms, RG59 is 75 ohms. So it can be the same or it cannot.
So RG58 is,
Your thin stuff for your CPU, your car radio
yeah,
is 58, that's 50 ohms.
right?
And so is your RG8, the big thick stuff that you may be running your 100 feet down from your antenna on your tower, or RG213. It's still 50 ohms, but
Okay.
it's twice, it's like the size of your thumb, right?
I just want to put a plug in for doing the tests online, because I wouldn't have known the right answer had I not got it wrong.
Yeah, definitely. When it slaps you in the face and says you got it wrong, you're definitely going to learn a lot more of it. So when you're sitting here, sometimes you can be like, I'm not 100% sure, and then it goes to the next slide, like, oh yeah, I was totally thinking that. But I mean, as you did with the Q codes, you're like, this was a lot easier when I had answers available. So
Well, I got this one wrong when I first looked at it. When I was doing the test a couple of days ago, I picked the wrong one and I got looking at it and I go, hang on, no, it's that one. You start reading it and you start thinking it through, but yeah.
Alrighty. What commonly available antenna transmission line can be buried directly in the ground for some distance without adverse effects?
Coaxial cable.
No, don't worry. Yeah, it's coaxial cable.
Yeah.
Perfect, yep. So this is because coax has a ground pass on the mesh around the center conductor, so which shields it. Alrighty. The characteristic impedance of a transmission line is This is one of those interesting questions that you're probably not going to know the direct answer. You're just going to know that 3 of them are wrong.
E.
E? None of the
I thought number 2.
Number 2?
I'll say 4.
What we get? Number 1. So.
So we go. Can't win.
So.
What do we got here?
Yeah, so the characteristic impedance of a transmission. Again and again, yeah.
This stuff is confusing for me. I hate it. Bob probably understands a lot more than I do, but.
Yeah. I'll admit, I'm up here, and then some of the time I'm like, no, that's not right. And then we see the answer, and I'm like, no, that one is also right. Wait, I'm wrong. Okay.
I asked my wife, I said, read the question in the book and I'll see if I can answer it. She said it's all impedance, reactance, and then, what was the other one she said? Capacitance.
Yeah.
She closed the book.
All right. So, next question. What factors determine the characteristic impedance of a parallel conductor antenna transmission line?
Oh, okay.
I like number 3, but
Number 3.
That's what I said.
All right. And we get, number 3. So, when they're talking about parallel conductors and transmission lines, they're talking about anyone that isn't coax. And frequency does not affect the characteristic impedance of transmission lines. So, it affects other things, but not the impedance.
I
So,
think they brought up under the ladder line.
yeah, so there are 3 types of parallel lines. There is plastic sheath, there's ladder line, and then there's open wire. I don't think anybody has any samples of them. Everybody looks at Bob.
Yeah, yeah, they're terms that are easy to mix up. The old television ribbon is what you call the plastic sheet.
The plastic, yeah.
What you called ladder line is what some people call a window line. It looks like the solid sheet, but it's got holes punched in it all the way along.
Is that a picture book?
And then the old the 600 ohm usually ladder line, which I used to call ladder line because it's like a rope ladder. Those are your parallel open line,
Yeah.
and as you say, it's the diameter of the line and the space between them that on the previous question.
Yeah. Yeah.
That
So.
affects the impedance.
Alrighty. What factors determine the characteristic impedance of coaxial antenna transmission line? The good thing is the answer is essentially the last answer, just describing coax as opposed to parallel lines.
So we're back to 1 again.
Am I good? Yep, number 1. So, yeah, nor is this affected, that isn't spelled right, but nor is this affected by the length of line as well. All of the answers in there seem to have something to do with either frequency or length of the line. Those are both wrong. So, alrighty. What is a coaxial cable? Oh man, we're going easy.
The first one. Yeah, the first one.
yeah, insulating wire material, yeah.
Yep.
With
So-
a hard wire, you can get copper. On the coax, can you get to the center can be solid, copper.
Mhm.
First one.
Or I read somewhere, and before I came over tonight, stranded.
Stranded core, solid core, yeah.
Yeah, okay.
We use stranded core in the elevator traveling cables because it bends better.
Okay.
Oh, I see, yeah. It would as opposed to solid, absolutely, yeah.
Yeah. And just to throw you guys off, there's even some that have 2 of them inside. So coaxial cable. Those are kind of fun. But anyway, you're not being tested on any of that, so let's move on. What is parallel conductor transmission line? Sorry for the size.
Number 2.
Number 2.
Number 1.
Okay. And we get number 1.
Number 1.
So it's 2 wires held apart side by side. So if they were twisted, they'd be called twisted pair, and they'd make a pretty bad transmission line because they keep canceling out each other's radio waves. The center wire inside an insulating material which is covered by a metal sheet, that's coax, and a metal pipe which is slightly wider than wavelength. No. If you have a metal pipe that's trying to do 20 meters, you.
No, it's number one.
Yeah. All right. Yep. Looks like a ribbon. So. What kind of antenna transmission line is made of two conductors held apart by by insulating rods? So this is specifically knowing the difference between what Industry Canada is calling open wire ladder line or twin lead in plastic ribbon.
Well, twin lead plastic ribbon is the answer. Number one.
Well, they're not rods, that's a ribbon. So I'd say, by the way they're wording it, open wire line.
That's correct, yeah, open wire line. So because they're specifically mentioning they're held apart by insulated rods, it's the two wires.
Is it?
So, quick diagram.
Yeah.
The three different types. I'll just draw the coax as well. So for coax, you've got essentially something that looks like this, and then you've got a sort of braided material, right?
Yeah, that's the sheath.
Yep. And then inside here, you've typically got a plastic insulator, and then you finally got the center pin,
That's correct, yeah.
right? For twin lead covered in plastic, they kind of look something like this.
That's like old TV wire.
Yeah.
Exactly like old TV wire.
Yeah.
So, you got plastic covering all of this, right? And this is all covered in.
Absolutely.
For what they call ladder line, same general design, but with one slight difference. So you got, what happens is, you got sort of holes punched out of it. So that this area is actually filled in, but you got holes in there, and then you've got your metal wires that stick out the end, right? So if you imagine this is a filled in plastic area, and then there's actual physical holes in it, so it kind of looks like a ladder. The one that sometimes can be referred to ladder line that they call open wire, with the way they describe it, specifically for their open wire, there is no plastic coating on the wire, and instead what you have is you have like little wooden or plastic spacers that they go through. So you have two that go through here, and then you got.
That's used for insulators on your antenna, the plastic spacer.
Well, so yeah, this particular line would be held apart with either a wood or a plastic spacer on it. So it looks almost like train tracks as opposed to this kind of looks like film.
Why do they call it open wire if it's rods?
So because what they're talking about is the wire not typically having insulation on it. It may be anodized, or not anodized.
Oxidized?
No.
Sometimes, yeah.
Yeah.
It's usually, what do you use? The copper covered steel, what's that called? Copper weld?
It's the type of.
Copper weld or something like that, yeah. It's just two copper wires, and then whatever insulating material you're using to separate it at that distance, yeah.
Yeah.
Yeah. So.
Does it make reference
Clothes pegs,
to
anything.
waveguide?
Clothes pegs.
Yeah, they
The wave
keep
guide?
it apart, eh?
Don't worry about waveguides. Oh man.
They make mention to it, but they never define it.
No, don't worry about waveguides. That's all an advanced
That's
topic.
advanced,
thing.
yeah.
So.
Yeah, but to me, I wonder, well, why do they mention it if they don't?
Just a confusion.
Yes, that's the very fact, the very thing. You see that in the book, and then you start to read the son of a gun because it's in your head.
You gotta remember the guys writing the book are not employed by the government, right? So they're trying to give you what's on the exam, but then they throw in they throw in stuff that they think that as a ham you should know, and then sometimes they just mention stuff when they probably realize they shouldn't have to when they read it. They probably like, we shouldn't have put that in, but
Yeah.
Well,
But yeah, don't
you
worry
don't know
about
what kind of
waveguides.
ham I am.
So yeah, the only reason number one was wrong is the plastic ribbon. But go back. What was number one? Yeah. So yeah, the twin lead, because they're talking about specifically the insulators. So that's why the first one is incorrect. So. Alrighty. What does the term balun mean? Now that we've heard it 400 times.
number one.
Number one, balanced to unbalanced.
That's it.
That is correct, yep. A balun is an electrical device that converts between balanced signal. This is two signals referenced against each other. They're balanced with respect to each other. And an unbalanced signal, a signal referenced against a ground. Any particular ground you choose. Because it's unbalanced with respect to each other. So one is at one particular potential, the other is at a different one. But the one that you're talking about is grounded, whereas the other one isn't. This unbalanced coax, so typically what they're referring to is an unbalanced coax, right? Grounded through the means of your transmitter to the ground in your house. And a balanced antenna, which is not grounded. to the same ground. It may be grounded for lightning strikes, but because it's not grounded to the same one, you have a balanced antenna, unbalanced coax that need to go through a balun to become unified. Questions, comments, concerns? Okay. Where would you install a balun to feed a dipole antenna with 50 ohm coaxial cable? That whole 50 ohm coaxial cable part is entirely irrelevant. Doesn't matter.
Number 3.
Between the coaxial cable and the antenna? So everybody says? Yep. Coax is unbalanced as the transceiver is grounded while the antenna is balanced using a being dereferenced against the transmission line, so you have to use a balun to connect the two. Alrighty. What device can be installed to feed a balanced antenna with an unbalanced transmission line? I wonder if it's triaxial transformer. So we all know it's a balun, of course.
Number 4.
Yeah. Yeah, no, and not really. So, it's a balun. Alrighty. A flexible coaxial line contains
Number 2.
Number 2.
number 2. Number 2. Yep. Pretty easy if you've seen coax before. So, alright. A balanced transmission line.
Is the answer in the question?
Not really. But so coax is unbalanced, whereas parallels are balanced. Yeah. So each of the different lines there are balanced wires because they don't have the grounding sheath around it, or mesh, whichever you prefer to call it. So yeah, remember there are 3 common variants in use: the open wire, the insulated, twin lead, and ladder line. And again, they come up with like 500 different ways to describe the parallel wires going with coating on them, or they're talking about one of those 3 variants, but they like to use different terms every time, so just try to learn some of the common variants and pray. Alright, a 75 ohm transmission line could be matched to the 300 ohm feed point of an antenna.
Number 4.
Number 4. Alrighty. We get? Yep, number 4. A trigatron is a pretty cool answer, though. I actually looked it up. If we go to the next one. Yeah, a trigatron is the last thing your radio needs. It's designed to switch extremely high currents. Essentially, it's a spark gap with a third electrode that allows you to create the spark across that arcs the power through it. If your radio had one of those, your electronics and your neighbor's electronics and everybody's electronics and then your probably neighborhood would go down. So...
They use one of those to make Frankenstein.
Pretty much, yeah. So, but, alright. What kind of antenna transmission line can be constructed using 2 conductors which are maintained a uniform distance apart using insulated spreaders? So you just have to think back to the parallel lines in which they're particularly talking about with the insulated spreaders.
Number 3.
Number 3?
Number 4.
Number 4. Answer is number 4. So they're again talking about those insulating bars that spread apart 2 wires, so they're talking about open wire.
Yeah, absolutely. Yeah. That's open wire.
Alright, insulated bar spreaders means open wire.
Yeah.
So, alrighty. Why does coaxial cable make a good antenna transmission line?
Number 1.
You can make it home, and it's impedance matches. No.
I want to see somebody make coax at home. Anyway, answer is, of course, number 1.
Yeah.
But it is can be used near metal pretty well. So, its impedance is 50 ohms, which is near most antennas. So it's pretty much the default.
This coax wire, it can be buried underground as well.
Mhm.
Yes, but you should have the type that is made to be buried.
Yeah, absolutely, yeah.
And not all of it, some of it could be
Yeah,
a little bit, but your direct bury is something like RG213 or...
yeah, it gives reference to it in the book, yeah.
Yeah. So, Oh, just a quick note as well on outdoor cabling, make sure you get one that's UV resistant. That'll just make sure that the sun doesn't slowly destroy the casing and expose it. What is the best antenna transmission line to use if it must be put near grounded metal objects? We just answered this one.
We just did. Coax.
Coax. Alright. Yes, again, because the braid is grounded, this means the coax is unbalanced but less affected by grounded externalities. So. Alright. Well, I gave the answer away on this one because I forgot to edit it. So, what are some reasons not to use parallel conductor transmission lines? Does not work well when tied down to a metal object, and you should use a balun, and may have to use an impedance matching device with your transceiver.
Absolutely.
Alright, I think we're coming up to the break soon, which will be pretty good for us. So, just taking notes so I can fix these when they go up online. So. Alrighty. Perfect. Alright. What common connector usually joins RG213 coaxial cable to an HF transceiver?
Number 1.
Number 1? Yep. Number 1. So F-type connector is what you typically use on your TV set-top box. We don't use that in amateur radio, typically because it's really bad. Yeah, the banana plugs are typically used on like test equipment. And what was the last one? If you go back? A binding post, yeah, no. Again, same thing.
We use those on parallel line.
Parallel line? Oh, okay.
The last
And
two-
power supply.
Oh, power supplies, yeah, that's the crank down one that you put a thing into. I didn't think we actually used that, but parallel line, I guess.
The PL259 connector.
Yeah, yeah. Alright, next up, alright. What common connector usually joins a handheld transceiver to its antenna? Which of these was not like the last one?
Number 4.
An SMA connector. Yep. Alrighty, yep, SMA connector. So it's the same thing that's used on your Wi-Fi. If you've ever had a Wi-Fi device that has removable antennas, it's the exact same connector. So. Which of these common connectors has the lowest loss at UHF?
Number 4.
Number 4. Nope. So, if we go to the next one.
I thought it was number 2.
Type N is great for up to 11 gigahertz. PL259 can begin having problems apparently at the 100 megahertz, but it's typically rated to 300 megahertz. As far as able to find out. A BNC can usually do up to 4 gigahertz, and SAM, I don't think that's right. Oh no, yeah, SAM. No, was it SAM or SAM? If we go back a couple ones, that was the one on the Wi-Fi routers. Go back a couple. SMA. All right.
Just spelling error.
Swap the two. Yeah, so the SMA connector can typically do up to 18 gigahertz rated, but some people claim they can go as high as 26.5 gigahertz. I really want to know what equipment they're using to test that because I would love to get some, but it's, that's how they're rated. So the N-type connector is pretty much the one you're going to use for a lot of high frequency work.
BNC is what we're going to use then?
Type N. So the only typical problem I know is that they're pretty expensive, aren't they?
Yeah, I think about 20. I think they're $7 or $8
Okay.
compared to the three or four.
Yeah. So. I know I recently picked up a PL259. It was around the $3 or $4 range, but I know N can be a little bit more, as $10 or so. But
A lot
yeah.
of people put the end connectors on the UHF. If you're running I've only got a VHF, UHF antenna up. You put an end connector on if you want to just to reduce your loss. You know, it's okay on VHF to PL259, but when you start getting up to the UHF band, if you got a long run of cable and stuff, you start getting a little bit of loss.
Yeah. Alrighty. If you install a 6-meter Yagi on a tower, 60 meters, 200 feet from your transmitter, which of the following transmission lines provides the least loss?
Number 4?
Number 4. Okay. And the answer is
Number 2.
213. So the general rule of thumb I can give, bigger number, less loss. That's not really true, not by a long shot. You'd have to look up an actual table. But for the industry candidate exam, bigger numbers means better, typically. So, yeah, generally not really the biggest number, the lower the loss over a distance. So, alright. Why should you regularly clean and tighten all antenna connectors? Keep them looking nice. I like them being pretty.
Number 4.
4 to keep their contact resistance at a minimum. We get? Yep. So any of the oxides, the rusts on any of the parts acts as a very good resistor. So we always want to try to remove that. So we're getting to the break soon. All right. TV twin lead transmission line can be used for a transmission line at an amateur station. The impedance of this line is approximately
3.
3. That was really quick, and I like it. So, yep, 300 ohms. So, it's just a memory task, but a pretty good one. Why should you use only good quality coaxial cable for connections for a UHF antenna system?
Number 2.
Keep RF losses low.
No, I like number 1.
Keep standing wave ratio of your antenna system high. Yep. Number 2. Yep.
Oh, I read that. I'm sorry. I thought that to keep the standing thing was part of the question.
No. So, yeah, as you get higher and higher frequencies, you get more RF being lost at particular points in the system. So for UHF, you want to try and keep your RF losses low by using good quality coaxial cable. So, yep. What are some reasons to use parallel conducting transmission lines, or conductor transmission lines?
Number 3.
Number 3. All right, here's what we get. Number 4. It will operate with a high SWR and has less loss than coaxial cable. So, I think this is one of our discussion questions. Oh yeah, okay, so I'm not exactly sure why the high SWR would be a really good thing.
Yeah.
Of course.
If you're going to use a single antenna to cover all the shortwave bands, like that monster I got a field day, you can use like a 130-foot antenna and just connect it to a 450 ohm line coming in, and then an antenna tuner. If you tried that stunt with a piece of coax instead of the open wire line or the ribbon line, your high SWR on the line would just pretty well kill the signal. Whereas if you use because your losses are so high on coax at high SWR, but the losses on a parallel line at high SWR are low, so you can get away with it.
Okay.
You can get away with one antenna that does everything.
So that's why it is. It's where you want to, as you said.
You don't want it.
No,
but if you have to put up with it, then your losses are almost nothing with a parallel line.
Okay. Yeah, so what he's talking about is if you want to, as he said, work every single band with one antenna, then you're going to go this route because you don't lose all that signal places where you have high MP or SWR standing in the line. So, alrighty. If your transmitter and antenna are 15 meters, 50 feet apart, but are connected by a 60 meter, 200 foot of RG58 coaxial cable, what should be done to reduce transmission line loss? All of the first part really doesn't matter.
Number 1.
Number 1.
Shorten the excess cable? Yep. So if you ever see that you've got lots of coax just round around like this, that's all being lost in RF energy. It has to travel through all that cable to get to your antenna. And wire is a very poor conductor, but it is, or resistor, but it is still a resistor.
Yeah, if you looked at my basement, you'd see lots of those loops.
Everyone does. It's way more work to actually cut and re-terminate, but yeah.
You never know when I'm going to want to move something.
That too, yeah. So over-engineering is the problem, right?
Yeah, I am, absolutely.
So, alrighty. As the frequency of a signal is changed, what happens to the signal loss of a transmission line? I see a really long answer.
Number 2, I think. I'm just guessing.
Number 2? Answer is? Number 3. Yeah, so... transmission line has a reactant. Transmission line has... I think I meant to say resistance. The transmission line has... reactant, all wire does. Those higher frequencies reacts... Okay, yeah. Oh, reactance. Okay. So basically when you pass any electrical current through a wire, it builds up a small magnetic field. This particular magnetic field at higher frequencies reacts slower. That is, you build the fields out and then it collapses slower. And essentially, over large distances, it accumulates. There's a lot of spell check in there. Sorry. But yeah, as you pass electricity through it, it builds up a small magnetic field. The higher the frequency, the more the field influences the RF in there. So at a lower frequency, it's able to expand and collapse at that particular frequency, but as you get higher, the field stays kind of constantly.
And you notice that, sorry, with Coax, with a high SWR on it, it's a lot worse at the high end of the RF HF spectrum than at the low end. It's worse on 10 meters than it is on 80 by a long shot.
Yeah.
Whereas again, the open wire stuff, yeah, the SWR is high, but you don't get the losses. So.
Yep. Alrighty. Alright. Losses occurring on a transmission line between transmitter and antenna result in
Number 3.
number 3.
Yeah.
We get number 3. Yep. Less RF power being radiated. That's what losses means. Alright. The lowest loss transmission line on HF is
4.
4.
You just said 4.
Open wire, yeah.
Answer is yep. Open wire line. So hard to beat wires with little or no reactive interference between them, except you must match the 600 ohm impedance of them to typically a 50 ohm antenna. So that is the one downside.
Or not.
Okay, I guess.
Just get away with it. You see?
Yeah, fair enough. So you also don't have to match the 600 ohms if you don't really care about how good it is. So, in what values are RF transmission line losses expressed?
Number 3.
Number 3, decibels per megahertz.
Yeah.
And we get decibels per length. So half right. Yeah, so it makes sense since the signal power is attenuated. So we're back. Hope everybody had a good break. Learned a lot of stuff from the demos back there. Alrighty.
Oh, hold on. It's not okay.
Alrighty. So we're gonna roll into section 8. Now onto antennas from transmission lines. First question. Which type of antenna would be a good choice as part of a portable HF amateur station that could be set up in case of an emergency?
Number 1.
Dipole. Perfect. Yep.
Do you have a picture of a dipole?
One on the table over there.
It's a single wire. Yeah, there's actually one on the table right there. So that yellow cable. Dipole is just a wire that can be wound much like an extension cord. I know a lot of guys have got it wound on those auto winding.
I know Alex has one on the table.
Yeah, exactly. No, I'm just saying like some of the solutions I've seen.
I was punning.
Alrighty. In a Yagi 3-element directional antenna, here we go, the blank is primarily for mechanical purposes. This is one of those questions that get a lot of mileage out because they're just going to ask you what each of those mean.
The boom.
The boom. We get the boom. Yep. The boom is just a pole it's mounted on. So, it's the name we go for. Alrighty, next up. Blah, 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 blah. Blank is the longest radiating element.
Number 3.
And number 3, driven element, reflector, we got.
Number 1.
Answer is reflector. Yeah, the reflector is longer than the driven element.
5% more sense.
Yeah. So see the videos online for more information. They will run you through Yagis like you've never seen before. Blank is the shortest radiating element. Director number 3. Yep. And finally we get blank is not the longest nor the shortest radiating connected element.
What's left?
I don't know, maybe it's boom. Of course, it's the driven element. So, and see the online videos for more information. Alrighty. What does horizontal wave polarization mean?
Got a lot to do with the Earth.
Number 1.
Well, they need some reference if they're talking about horizontal. Maybe to the operator, you lie down, waves change. Alrighty.
Number 1.
Number 1, the electric and magnetic lines, of course.
Number 4.
Yeah. So when we're in electronics and radio specifically, we only care about the electronic field. We don't care about magnetic. We go to the next one. Yeah, so we only worry about the electric field. The magnetic field is just a secondary element that happens. So as we move the electronic field, in this case, perpendicular, parallel to the Earth, the magnetic field moves vertical. But we don't actually talk about the magnetic field because that's induced by the electronic field. So the magnetic field is 90 degrees to the electric field. Perfect. Which electromagnetic wave polarization does a Yagi antenna have when its elements are parallel to the Earth's surface? Heliacal. That's definitely it. Alright, the answer is? Horizontal. Yep. So Yagi is just like a dipole. Yep, with reflectors and directors. So. Which electromagnetic wave polarization does a half wavelength antenna have when it's perpendicular to the Earth's surface? I just wanted to define whether or not you know what
One.
perpendicular and parallel mean.
Vertical one.
Yeah, so yeah, vertical. Perfect. It's not even a trick, just straight up. Polarization of an antenna is determined by
Number 3.
number 3. Longest answer wins? Longest answer wins. I think we get the point. Let's move on. Alright, an isotropic antenna is and we get a hypothetical point source. Though an infinitely long piece of wire would be very fun. Alright, so yep, an isotropic radiator does not exist. There's no such thing. But for companies that like to inflate their numbers, that's a very fun source to go to. So, what is the antenna radiation pattern for an isotropic radiator?
Number 2.
A unidirectional cardioid? Number 3, a sphere. Answer is a sphere.
3.
So from a single point source, you have to imagine a single point smaller than anything imaginable, what we typically call a singularity, and it just radiates in all directions evenly. So, yep, it radiates perfectly in all directions. If an electromagnetic wave leaves an antenna vertically polarized, it will arrive at the receiving antenna by ground wave.
Vertically polarized.
Number 3.
Yep, vertically polarized. So yeah, only ionospheric interactions cause polarization switch. So, and then we learned that last week. Alright, compared with a horizontal antenna, a vertical antenna will receive a vertically polarized radio wave. I love they just keep coming back to the same question because it's really the only standardized thing we fully understand about antennas. So.
Number 2.
Number 2, if the antenna changes the polarization.
No, compared with horizontal. Vertical antenna will receive a vertically polarized radio wave. Is there any difference? You're talking about vertical, won't do vertical.
Compared with a horizontal antenna, a vertical antenna will receive vertically polarized radio waves. It's greater than a horizontal antenna without any comparative difference to a horizontal antenna, weaker than a horizontal antenna if the antenna changes polarization.
You're talking about the same waves being sent and received.
So the answer is
Number 2.
it's greater strength.
Well,
So
restricted what?
this is so it's an interesting way they're playing with the English up here.
Yeah, they are complaining, they're not.
Yeah. So they say we're sending a vertical antenna will receive vertically polarized radio waves. If we send it to a horizontal antenna, the signal strength will be greater because we're receiving it at the vertical rather than horizontal.
So anytime they mention two different things in the question, you gotta figure they're sending two different things.
Yeah, it's like half English test, half.
Yeah.
Yeah.
All right, moving on. This is why we polarize our radio waves. Yeah. So, well, not why we polarize it, but why we have to care which polarization it's in.
So if you send vertical,
Mhm.
and it's received horizontal,
Well, they can still receive it.
Mhm.
Unless
It's just like they're
unless it's
comparing
satellite
it.
TV,
So
but
like
you can't
the
receive it
horizontal
because
one
of that.
can technically, but the vertical one will do it stronger.
yes,
That's literally what
absolutely.
it's saying.
Yeah.
So when I read that, one thing I got thinking about was the little handheld radios. So if you put your handheld radio sideways, are you going to get less reception than if you put it vertical?
Yes, actually.
Yeah, yeah, okay.
Yeah.
Yeah, okay.
So yeah.
I'm gonna get like a VHF radio
Yeah.
where it counts.
Yeah, and if I was talking to you and you had yours vertically and I had mine,
Yep, it'd be worse.
yeah, it would be worse.
You have to be far enough
See how he's
apart that
holding
you
this?
don't-
Yeah.
not full strength.
Yeah.
Yeah,
This one's number
yeah,
3.
so common sense, you have the pointy end
Or
up.
the frequency.
Yeah, both all the time.
Yep. So if an antenna is made longer, what happens to the resonant frequency? We had number 3, it decreases. Answer is, it decreases. Yep.
The higher the
So-
frequency, shorter the antenna, vice versa.
Yes. Exactly, yeah. So frequency and wavelength are inversely proportional. As one increases, the other decreases. So very straightforward. If you shorten an antenna, you shorten the wavelength which is resonant, and the frequency which is resonant increases. So, because frequency and length are inversely proportional. Perfect. Adding a series of inductance to an antenna would... Number 2. Increase the resonant frequency. And we get decrease. So if we remember what an inductor is just a piece of wire. So we lengthen the length of the antenna essentially.
Oh yeah, yeah.
And we get-
backwards, yeah.
Yeah, decrease in resonant frequency because it's now longer.
Yeah.
So, yep, an inductance is a coil of wire, so adding inductance in series with an antenna means that you're lengthening the antenna. The longer the antenna, the lower the resonant frequency. So, the resonant frequency of an antenna may be increased by...
Shortening the radiating elements.
Sounds about right to me. Yep, shortening the radiating elements. Yep, same thing. Frequency and wavelength are inversely proportional, so if we trim some off the end, frequency goes up. Alrighty. At the end of a suspended antenna wire, insulators are used. These act to... This is one of those weird ones that they're not...
Yeah.
Yeah.
Yeah, that's true.
I like
to think of it. It didn't say which direction or how holding it.
Yeah.
I like the one where you increase the effective antenna length.
Okay.
Number 3.
Number 3, alright. This is all over the place. What we actually get is... Number 1, limit the electrical length of the antenna.
Yeah.
This is a terrible question.
It's
It
a
is.
terrible answer. That,
Yeah.
That's only if,
Well,
the
if
thing
we-
that's holding it up is wire and the antenna's wire, and you put an insulator between it, it would
And it's the end of it.
effectively make the entire antenna system shorter.
Exactly, yeah.
That's the way they're thinking, but they don't tell you that.
No.
Sorry.
Yeah, so we're talking about the insulators when we're attaching it to something like a conductive pole, like a flagpole or a laundry pole or something, or an antenna tower, and a metal pole like a wet tree or something like that. So the insulator means that we can shorten the antenna, and technically it's slightly shorter. It's a sneaky question.
It's a two-way question.
Back up again, unless that was the question.
Yeah, of course.
Yeah. At the end of suspended antenna wire, insulators are used. This is an act to limit the, and of course number 1 would be limit the electrical length of the antenna.
Yeah.
Increase the effectiveness of the antenna length.
So it does. So again,
We'll
it's
find out.
you just start eliminating the ones. It
Yeah.
doesn't increase the effectiveness of the antenna. It can't allow the antenna to be more easily held vertically. I mean, like technically, now that you have an insulator on it, you could hold it anyway. But
Yeah, right.
that's not really why we're doing it. And prevent any loss of radio waves by the antenna. That makes no sense. We want radio waves to leave the antenna. So
Yeah.
you just have to deductively reason that one. Alrighty.
Yeah, limit, okay.
So, one solution to multi-band operation with a shortened radiator is the trap dipole, or trap vertical. These traps are actually... I could have shortened it to what is a trap, but...
Number 3.
Coil and a capacitor in parallel.
Mm-hmm.
Survey says, indeed, coil and a capacitor in parallel. They act to lengthen the antenna, but only at specific frequencies. So, what is a parasitic beam antenna? I really make you read these ones.
Number 3?
Number 1.
Number 1, number 3. And we get number 1.
Oh, shit.
An antenna where some elements attain their radio energy by induction or radiation from a driven element. So the parasitic beam they're talking about, it's just another name for the Yagi Uda. So, yep. How can the bandwidth of a parasitic beam antenna be increased?
Number 3.
Closer element spacing?
Number 4.
Larger diameter elements.
Yeah, what's bigger the better.
Yeah.
So we get, yep, larger diameter elements. So, discussions.
On that?
Yeah, I didn't know how to explain this and why it works.
Is there a limit on how big you can make those things?
I can't give it to you electronically, but I know that when you increase the diameter of the wire on an antenna, that it has a wider bandwidth. It will resonate from a higher frequency and a lower frequency than just a thin wire. If you can make one out of 45-gallon drums,
Yeah, that's what I'm saying. Is there a limit to this?
yeah, but they've found a way around that. You look at the old movies and the old pictures, they used to have a dipole with a wire up the center, and then instead of a wire across, they had like 4 wires going across. That was the diameter of a 45-gallon drum going across. You see that like on the Titanic, those kind of antennas in the old days. And they had they did that for a wider bandwidth.
Yeah, I know one of the ones typically used a lot when you're doing wideband applications. It's called the squirrel antenna. So the squirrel cage, basically you run a vertical pole and then around them you've got like what essentially look like wire frame drums. So they've got 2 hoops on the top and then vertical bars along them. That apparently increases the amount of bandwidth that an antenna has, but...
I've seen that, but I've never had any experience with it.
Yeah, me neither, so... Yeah, bandwidth, I don't even think advanced goes into bandwidth too much of antennas and calculating things electronically, so... Alrighty, now we know. Yeah, there we go. If a parasitic element, slightly shorter than a horizontal dipole antenna, is placed parallel to a dipole, 0.1 wavelength away from it, and at the same height, what effect will it have on the antenna radiation pattern? That is a lot of words to describe something simple.
Does a long answer work here?
I don't think so, because 3 of them are pretty long. The 4th one's got an extra word in it, I guess. Number 4?
Yes.
Okay, answer is?
Long answer.
Indeed, number 4. A major lobe will develop in the horizontal plane from the dipole towards the parasitic element. So.
The key was a bit shorter.
Yeah, so yeah, exactly. This question is just discussing the radiation pattern of a Yagi with respect to a director, the shorter element. Right?
Can you define a parasitic...
An 80 meter be twice as big again, and then 160, I mean, you need like, stadiums to carry those sorts of antennas. So, yep, straightforward, fair enough. What does antenna front to back ratio mean in reference to a Yagi antenna? Number 2. Answer is number 2. Power radiated in the major radiation lobe compared to the power radiated in the exact opposite direction. So how much is going forward as opposed to back. Perfect. Remember that not all the power comes off the front, still some manages to escape through the back. So, although it's directional, it's not perfect. What is a good way to get maximum performance out of a Yagi antenna? Use a reactance bridge to measure the antenna performance from each direction around the antenna.
An RG58?
RG58 transmission line? Avoid using towers higher than 9 meters. What we get is optimize the length and the spacing of the element.
Did you see that one up there?
Yep. So if we optimize the length and the spacing of the elements, that's the best way to do it.
I must be tired.
No, it's fine. It's been a long night. But, yeah. All right. Yep. Yakis are all about these 2 qualities. So, the spacing between the element on a 3-element Yagi antenna, representing the best overall choice, is blank of a wavelength. 4? Answer is? And 1.
Really?
That's what they want.
Wow.
So, because I guess what they're getting at is with 10, maybe it's a little bit tough to get it to that specification.
So 0.20 represents,
The wavelength distance between elements. So when you calculate out the wavelength of the antenna, right?
Yeah.
It's going to be half of the wavelength is going to be the distance across that your elements are, right? But when you're spacing out the elements, that distance is also important in order to get that perfect constructive and destructive interference pattern between the two. So what they're saying is the 0.1 would be great if you're really trying to like have it tight and tolerant with a nice flexibility. But if you move it out to 20, apparently it's going to get better gain and reflectivity.
Oh, excuse me.
As you keep going, it starts to drop off. The amount of money you're paying to get extra material to make it longer isn't worth the amount of extra gain you're getting out of it. Is effectively what they're getting at.
0.20 represents the actual width.
The length, front to back.
Or length, sorry, okay.
Yeah. So because this would be this distance here of
Yeah.
the driven element, that would be equal to 1/2 of a wavelength. What they're talking about is in here, they want 0.2 as a really effective distance between those two elements. So,
Yeah, absolutely, okay, yeah.
yep.
Very good.
Yeah, so that's the best we can get at. If the forward gain of a 6-element Yagi is about 10 decibels compared to an isotropic radiator, what would the gain of 2 of these antennas be if they were stacked? This is a decibels question, not really an antenna one.
13.
13? Yeah. So that's 13. So what happens is it doubles, but this means we only get a plus 3 dB change, not a double from 10 to 20. Because if we went from 10 to 20, that would be an order of magnitude change, remember?
Is that in the book?
Yes.
Yeah.
Yeah. So,
I ran out at 8.3, I think, 8.3 or 8.4. I didn't get all the way through.
okay, actually if we go back, yeah, that's section 8.10.
Yeah.
So,
Yeah.
all right. Moving on, section 8.5. If you made...
I want you to know I was working on impedance.
Yeah, don't worry, it's a tricky subject. It really is tricky. But the good news is calculating wavelengths is just one formula, right? Or 2, I guess, 2 numbers. If you made a half wavelength dipole antenna for 28.150 megahertz, how long would it be? It's fun to see everybody know with a calculator.
I forgot the number. 280 something, what was that?
286.
286.
Yeah.
Really wrong answer.
28.55.
28.55?
Holy shit!
Back to the instruction manual.
No, I come out right. It come out good.
So what'd you do with the equation?
Let's go over the equation again, see if I get this. So we're starting off with
Change from horizontal to downward sloping. It approaches 0. What is 0 impedance antenna? It either increases or decreases, so 50-50 says it increases.
enough of this.
No idea why.
Nope. Okay, so I figured maybe somebody would be able to explain it. I just need to know those 2 questions. It decreases and it gets closer to 50 ohms. So, all right. In which of the following transmission line? Which of the following transmission lines will give the best match to the base of a quarter wave ground plane antenna? As we discussed before, it's a pretty common number.
Number 1.
Number 1, 50 ohm coaxial cable. Bingo. Yep. Coaxial cable. Most antennas are 50 ohms impedance. You really have to go out of your way to find something other. So, all right. Next up, the main characteristic of a vertical antenna is that it will require a few insulators. I mean, technically, I guess you only need one at the top, but all right. What do we get?
2.
Yep, receives signals equally well from all compass points around it. So, this is a rewording of the roof antenna question. So, asking the same question twice. Moving on. Why is a loading coil often used with an HF mobile vertical antenna? And we get to tune out capacitive reactance. I think this is another discussion one, because, yeah. Oh, no, okay. HF antennas work better when they're away from big chunks of rolling metal. It's true, but... go back. See, why is a loading coil often used with an HF mobile vertical antenna? I would figure the answer is mostly because you can't put a full HF wavelength on top of your car. It's just too big. But...
It matches the antenna that's not a quarter wavelength, for instance, to your coax. And if it's a 5/8 wave antenna, it has to match the impedance at the bottom of the antenna to the coax where it's joined. And that the impedance is not 50 ohms because it has capacitive reactance. So with a coil on it, it combats that.
Fair enough.
Coil on opposite brings it back to 50 ohms.
Yeah. Okay.
I've never seen an antenna like that. You got 3 coils in that thing? One's for matching at the base, one's for 2 meters and 440, and there's another one on there for something.
Oh, mine?
Yeah.
Yeah, no idea. So, it works great. So, yeah, see, again, this is one of those things that you're like, wow, we're learning all this antenna theory, and then you're like lazy, and you're like, what's cheap and effective? So, this guy? All right, perfect. All right, what is the main reason why so many VHF base and mobile antennas are 5/8 of a wavelength?
Number 1, then.
The answer is? To number 4.
No. Our 5/8 wavelength, VHF, the angle of radiation is not high. That's a quarter wave. That's absolutely wrong.
Okay.
I thought it said it moved it up to the antenna.
Angle of radiation is low on a 5/8 wave antenna. That's why you should never use one on a sailboat. The mast tipped over, and have one up to the sky and one down in the ocean. You should use a quarter wave on a sailboat, for instance.
We can double check it, but this is the one that I'm pretty sure they use. Again, if it isn't, I will send out an email, I guess, and let everybody know. But yeah, that's the one they're given.
It's a quarter wave that gives an excellent recovery.
Okay. So there's a practical application and testing application.
Yeah, because the 5/8 squashes.
Mm.
Hold on, I'm just writing it down.
Okay. Yeah. So we'll write it down and we'll double check on the answer for that one.
And yeah, it's number 3 should be right.
Number 3, the angle of radiation is low. Okay. Next up we have... Yeah. Not sure why I'm unfamiliar with 5/8 antennas. That's... Okay.
You own one.
Which what? I know. I own one. I should probably research that. See what...
They showed it. It was up higher on the graph,
Yeah.
but it was also broader.
That's
And the quarter wave squashed.
How many directly driven elements do most Yagi antennas have? It's none.
Yagi. What the hell's a Yagi antenna?
That's that 3-element or more single line.
Like an old TV antenna?
Yeah, it's like an old TV antenna. So we get 1, yeah, which is technically 4, but yep, only 1. Yeah, none. That makes sense. Like no antennas. All right. Approximately how long is the driven element of a Yagi antenna for 14.0 megahertz? This requires 2 pieces of information because they don't directly tell you whether or not the Yagi is full wave, half wave, or quarter wavelength. But they're expecting you to use what is the common version of a Yagi built to.
Aren't Yagis small antennas?
Not typically, no.
The radius are 17 feet long or longer?
17 feet. I guess. Not really.
All these questions I'm going to answer.
Yeah.
Without doing
Go
calculations.
through the, go through
Okay.
the real, they're half wavelength normally. But sometimes you put to the now.
So if we're gonna calculate it, what we have to know is that the Yagi that they're talking about is a half wavelength Yagi. But yeah, as Bob said, you're typically gonna put a loading coil in something that's really massive to shrink it because you don't want like a 40-foot Yagi antenna on something. It'll be absolutely massive and the whole thing will just. But yeah, so the answer that we get here, if we divide 100 and, I guess it's below 30 megahertz, so we need 286 divided by 2 gives us 143. 143 divided by 14 gets us something in the neighborhood of... Perfect. 10.12. So, and if we get... Yeah, don't forget the deriving element for Yagi, most commonly half-wave dipole. So, it's one of those questions they should really state that they want a half-wave dipole Yagi antenna, but they assume that Yagis are always built half-wave for some reason.
I hope that's not on the test.
Oh, that's on the test.
Yeah. We're in trouble.
Alright. Approximately how long is the director element of a Yagi antenna for 21.1 megahertz? This is brutal because I don't even think the textbook goes into calculating director and reflector elements. So the only real way to know it is calculate what the actual one is and then either smidge it up or down for the particular one. There are calculators online that do that, but they always seem to be different in the answer they give because everybody likes to make their Yagi slightly different for some reason.
So is it 286 divided by?
So we're doing half wave again, so we
Yeah.
need 143 divided by 21.1. We'll get us something like 5, I would assume.
Okay,
It's
so
140.
143 divided by 21.1 is 6.7.
But 286 shouldn't it?
6.7.
be?
Yeah,
And
so how long
because
is
it's because the director's shorter, it's less.
It'd be 5%,
5%?
isn't it?
5% less.
Okay. So 5% less would get us, which would we get? 6.4. Because the original answer was
6.7.
6.7.
That's the closest.
So 6.7 would be the driven element, and because we want a director to be slightly smaller, we shrink it down to get 6.4 by about 5%. Okay. Half wave, remember. They don't include a quarter wave or a full wave. Oh yeah, so if we go back to the answers, the 12.8 and the 3.2 would be if you thought the Yagi was full wave or half wave. So be careful of that. Yeah. Approximately how long is the reflector element of a Yagi for an entirely different frequency, of course? Kind of interesting, because if you know that they're doing the full wave, half wave, and quarter wave on here, you can just guess. And I would say that the answer is probably going to be 4.88. That's probably wrong.
I was thinking 5.33.
5.33? Yeah, that'll probably be because you need to go up. So the answer is 5.33. Yeah, because it needs to be bigger for the reflector.
I just guessed.
Yeah, it's a 25% effective method. So yeah, so 186 should be 143 divided by 28.
Where is that 280? That 286, is that a common number?
It's just like a number in the formula.
Yeah. So
That's a constant though, is it?
Yeah.
Yeah,
It
it's
is, yeah.
constant.
Yeah.
I think it has something to do with the speed of light, and then because it's in megahertz, you can drop it down from the basically 300,000 meters per 300,000 meters per second, 300,000. Because you're using megahertz, you can drop it down to 300, and then because it's not exactly 300 meters per second, because we don't live in a vacuum, thankfully we get to breathe air. The number is slightly slower, so you get 286. So, yeah.
Well, yeah, we're gonna have to do something with this. Look at the answer I got with that one.
Oh, it gives you 10 and then 50 over 286. So if you could do that math in your head, you're good.
Surely that must have somewhere to turn it into decimal.
I would think so, yeah. But it's only got like...
I struggled at home with it. That's why I came tonight. That's why I brought it, because I thought to myself, why can't I see this, you know?
I've never seen one in decimal.
And I did absolutely what Alex said. Just buy a $10 calculator. That was $11.43.
See there? He said 10.
You pay too much.
Absolutely.
Let's see. Okay, what do we got? And or. So it's got like and or, XOR, not, sine, costant, stow, recall.
First scientific calculator.
Oh, hey, there we go. Okay.
You got
So,
it?
yeah, the button you need is this button down here, change. So if you
Okay.
press that, it converts it to a decimal. So if you try the equation again,
Okay.
and it comes up with the...
Just hold it, we'll do it again.
Yeah, of course. So use
286.
No, use
143.
286, do 143.
Sorry?
Do 143 because we need half
his
wave.
mistake.
Oh, half wave, okay.
Yeah.
Okay, so it's correction. 143
Divided by...
divided by
28.1.
28.1. And that equals
Change.
5, so we get 25 over 281.
You hit the change button.
And
Change.
oh, there it is, okay.
Yep.
1430 over 281. Oh, you changed.
Hit change again?
What'd you change it to?
Hold on, no, hit it again. Oh, you hit it twice.
Yeah. So I guess the first time it converts it into a single fraction as opposed to a side.
single fraction, yeah. 5.9.
Yeah, 5.9, so we get 5.8.
Yeah.
So pretty close.
Well, that's cool.
All right. Glad we figured that out. Alrighty.
$11.43.
Get you the power of fractions and dot matrix displays. And calculators are way cheaper than they used to be. So. Alright, what is one effect of increasing the boom length and adding directors to a Yagi antenna? The second part just gives it away. Weight decreases. Wind load decreases. It's kind of interesting. They're giving you like answers to things you should be aware of. Like if you add more directors, it becomes heavier, and in a wind, it will pull down easier. So, obviously, gain increases. So, farther from parasitic interference and more directivity equals more gain. So, what are some advantages of a Yagi with wide element spacing?
Well, if I knew the workings of a Aggie antenna, I would say number one, because it's the high gain, you have less tuning.
Answer is, indeed. Yeah.
Oh, it's
High
just
gain?
guess again.
No. Yeah, pretty straightforward. I'm not actually sure what the disadvantage are of having it so tightly spaced, or increasing the spacing. Sorry.
The disadvantages?
Yeah.
It's just weight, size, money.
No.
Wind, the wind, wouldn't it be?
Wind. Yeah. It's just weight. Yeah. Weight. And size.
Somebody say money?
Yeah. Unfortunately, antennas. They do contain quite high-grade aluminum typically. So. Yeah. Oh. All right. Why is a Yagi antenna often used for radio communications on a 20-meter band? I don't even know why they tossed in 20-meter band. It could just about be any band.
Number one.
Provides the highest possible angle of radiation for the HF bands. Answer we get is, so it helps reduce interference from other stations off to the side of your head.
Yeah, because it's directional.
Exactly.
Yeah.
Everything else is talking about an omnidirectional. So, or at the bottom they're talking about it being cheaper, less expensive, and easier to erect. Anything? No.
No, it's just normally, not really a 20-meter thing, but...
The radio wave propagated from this element is going to be at this part when we start broadcasting again, but behind here we're going to have a maximum out the back while a minimum is coming in, which leads to low signal in the back end. Again, definitely watch the video. Seeing my drawings up here does not do this justice, but seeing the animation in those, it's fantastic. You will learn pretty much everything you need to know. Same thing with the front radiator, but we're going to move it slightly out farther so that it's not out of phase, but instead in phase. So that when we build up that magnetic field, and then we drop the magnetic field, it's going to then constructively fire it out the front. So, as I said, the animation, once you watch it, it'll totally make sense, but that's the best description I can do with a whiteboard. So, alrighty, moving on. Yeah, so it's just discussing this. Same question, we're just talking about another element. So I'll give you a few seconds to read through. Looks like everybody's got their answer, and the answer is number 2. Yeah. So we're talking about the reflector here. So this one's the same, but again, the reflector because it's a slightly longer element. So the property of an antenna, which defines the range of frequencies to which it will respond, is called its number 1 bandwidth.
Yeah.
Mm-hmm.
Yep. Indeed, it is called the bandwidth.
Yep.
More bandwidth, more utility. Pretty straightforward. Approximately how much gain does a half-wave dipole have over its isotropic radiator?
Number 2.
Number 2.
Oh, wait, no. Number 4.
Oh, 2 to 1. So, just a quick way to describe this. So if we imagine these are the antennas running, again, we just have to imagine that I've essentially drawn like this, but from the side, so we flipped it that way, all right? If we have our single dipole, right, we've got a really long antenna running through this point. Off the side, our radiation pattern kind of looks like this. And from the top, we essentially have something that kind of looks like this, right? What's happened is it's taken all of the RF energy we normally fire at the ends and squished it into the middle. So it's nearly twice as good through the middle, right? So it's mostly because the pattern for the dipole has 2 lobes or 50% concentration from the full sphere. So,
Which
Kinda
is
makes
not good.
that's fantastic actually.
Is it really?
Go back
So-
to the question again.
Yeah, of course.
Yeah. Oh yeah. Okay. Yeah.
Yeah. So again, it's not a perfect double. A perfect double would obviously be, 3 dB. I thought that was negative 3 dB. I was like, that's not right, but no, so it would be a full 3 dB. The main reason to know this is because some, I don't want to say unscrupulous, but some vendors who really want to boost their numbers will say, well, compared to an isotropic radiator, an imaginary point source that nobody uses, ours is 30 dB better. And you're like, wow, that's amazing. And then you realize, well, 2 of those dB come from like not dealing with a dipole. So, but yep.
So he's a shoe salesman.
Yeah, kind of, yeah. So, what is meant by an antenna gain? I'd say long answer works here, but they're all really long.
Yeah.
So. Three?
Yeah.
The numerical ratio of the signal in the forward direction to the signal in the back direction. Answer is number 2.
Ooh.
Numerical ratio relating a signal strength of an antenna to another antenna. So the one that was number 3 was front to back
To our
ratio.
own self.
So we move on. Yeah, the gain is either of a dipole, or if the vendor is a little less scrupulous, an isotropic radiator. So typically when you see the gain of a particular antenna measured in decibel, if they do dBi, they're talking about the isotropic. If they do dB and then with respect to a dipole as a footnote, then they're doing it that way. But it's always to another antenna. In free space, what is the radiation characteristic of a half-wave dipole? We drew it. It's over there. Okay, and the answer is? Fabric, yep. Minimum radiation from the ends, maximum broadside. So, it sort of shoots it out the middle if you think about it that way, because it comes off the long side of the antenna as opposed to the actual point end part of the antenna.
Well, that's a poor choice of words. Broadside, but it comes out of the center?
Yeah, well, because it doesn't actually come out of the very middle, like the feed point, it comes out of the whole side of the antenna. So, an easy way to kind of think of it is think of the surface area that the side of the antenna has to the point. So if we look at like, the point of the antenna would have a surface area like this, whereas the side of the antenna has all of this to play with.
Absolutely, yeah.
So you get more signal off the side.
That's where you get it when it comes around.
Exactly.
Absolutely, yeah.
Yep.
Okay.
All right, next up. The gain of an antenna, especially on VHF and above, is quoted in dBi. The I is an expression stands for
Number 2.
ionospheric.
Is that? No, or is it, no, iso, no.
Isotropic, yeah. So
Yeah,
it's number 4.
Number 4, isotopic, yeah.
Yeah. So ionospheric, yeah. Although isotropic is ideal, yeah. So I say ideal in the sense that it's like a perfect sphere. But yeah. Anyway. Okay, here we go. The front to back ratio of a beam antenna is undefined.
Number one?
Number one, the ratio of the forward power at the 3 decibel points to the power radiated in the back direction. Alright, and so we get is... So it's the ratio of maximum forward power in the major lobe to the maximum backward power radiation. So, just to draw the radiation power for a directed antenna, if you remember, we've got essentially our, I'll just draw this, slightly longer element, slightly shorter element on a Yagi, right? We get like a really big one up the front, we get a little tiny one back here, and then we get sort of like 2 spikes off the back. Kind of looks like a bit of a pacifier shape or a plane or something similar to that. So what they're talking about is the amount of power out here to the amount of power in here. So if they're talking about a forward to back ratio, that's talking about the size of the antenna lobe, essentially, if you want to consider it that way. So, and the relative
How long
size.
are these things?
It depends on the antenna. So if you had 0 gain, like a 0 decibel antenna, which would be an isotropic radiator, then there would be 0 forward to back ratio.
No, I meant how far out do they go to measure these things?
Oh.
You don't actually, it's just a pictorial representation.
Yeah, no, but they do actually measure them, don't they?
Yeah,
With
you
a-
can,
with
it's
a
measured.
meter to go around and they can measure the field
It's-
strength, right?
You can measure with a meter, and on a chart it's measured in decibels.
Yeah. So
But that signal goes to Europe or to Russia or whatever. It's not a,
yeah. So
it's not in feet.
to answer the question, one of the main ways they'll typically do it is they'll take a really big field, and in the middle they'll place the little antenna. I'll just draw it here, right? And they'll have a bunch of recording stations, essentially in a circular fashion. They don't have to be if you use a bunch of mathematics to figure out how far you are. But then they'll broadcast a signal, and they'll measure how much strength they read at each of the stations. So you might get something like a 3, a 4, a 6, a 9, a 9, a 6, a 4, a 3, a 2, a 3, a 3, a 2. And then they plot that, so you get 3, 2, 3, 3, 2, 3, 4, 5, 6, 7, 8, 9. And so you end up with a shape kind of like that, except I've poorly drawn it. And this is what they plot when they're actually doing that lobe chart, because they're measuring how much signal strength they had at each of these
So it's
locations.
just an arbitrary, and you could just take any field, do that sort of thing, and then you can plot your graph from it.
Exactly. Yeah.
Which,
That's a really poor antenna. It all apparently leaks at the right side, but I think it kind of illustrates it. All right.
Somebody's got a tower sitting there and
for size directional driven arrays.
The correct term for a beam antenna is multi-element parasitic directional driven array. Yeah, who cares? Moving on. How do you calculate the length in meters feet of a quarter wavelength antenna?
did you change your font?
Yeah, so it automatically scales it depending on how wide or tall the text is. Sorry, it's a little tiny there. So either divide by 150 by the frequency, divide 71.5 by the frequency, 468 by the frequency, or 300 by the frequency.
No idea.
4 300? Alright. So the answer is 71.5. Don't worry, we'll break it
What are
down.
we doing?
So we're calculating how long an antenna should be for a particular frequency. So if we remember back to the textbook, there are 2 equations we use for calculating the length of an antenna based on the frequency that we want to achieve with it. If our frequency is above 30 megahertz, we divide 300 by the frequency.
Oh yeah, that formula.
Exactly. And if we want below 30 megahertz, then we divide 268 by the frequency. Industry Canada, for some reason, doesn't make this distinction. They always go with the 286. But if you're actually building an antenna, probably better to go with the more accurate figures. Technically, this number changes over the frequency, but the biggest change is in that 30 megahertz shift. So, anyway, so when we divide, because if we go back, what we're looking for is a quarter wavelength antenna. So that particular format, dividing 286 by the frequency would get us a full wavelength antenna. We want a quarter of that. So 1/4 of 286, if we go forward again, a quarter of 286 is 71.5.
So we use the formula and we know the 75 isn't there, and we can know it's not that.
Exactly. Yeah. Yeah. So there we go. But it will be important because a lot of the questions are going to do the same sort of thing. So you're probably going to want calculators if you have them tonight, because we're going to be starting to get into calculating distances for your antenna. But if you made a quarter wavelength vertical antenna for 21.125 megahertz, how long would it be? Anyone bring their calculator?
Yeah, I got mine.
Okay.
Somewhere.
Cool.
We're gonna get a course.
It works.
So, does anyone just want to walk through how you would do this?
Sure.
Okay. So,
Okay, go ahead.
okay, yeah, I was like, go for it, and then you said sure, so I was like, all right, I'll take over. So if we're doing a quarter wavelength, we want to take the magic number, 286, and we want to divide that by 4, which gives us a quarter wavelength, which also brings the number down to 71.5. We then divide 71.5 by 21.125, because we divide by the number of megahertz, and that gets us, I think it's 3.6? Or no, 3.3. I think it's 3.37 or something like that. So, am I close? We take 71.5, divide it by 21.125, we get. If we just go to the next one. Yeah, so 3.36. I'm pretty good. I like that. And we go to the answer. So again, yeah. 71.5 divided by 21.125 equals 3.38. So, which, when you do a little bit of rounding and some of the numbers don't quite work out, it's close enough. So, but if we go back, you can actually see that the answers, because we got 3.8, we know that 3.6 is pretty close, but they'll give you something like 3.6 just to really put it on edge. They'll do 6.76. I mean, that would actually be entirely correct if it were half-length dipole, and the 7.2, again, I guess just to mess with you. So, I really like messing around.
So you're doing. This is not working out.
71.5 divided by 21 point.
Divided by.
Is the calculation on?
No, that's right.
No?
I checked it.
What are you getting?
3 over 3,
3.38.
Oh, 3 over 3 85ths. Yeah. 85ths. Sorry.
So we could, this is what I'm getting.
Oh, it's got it in fractions for you. Yeah,
Yeah.
so 3 and 31 over 85.
Turn it to decimal.
Are we...
So turn that to decimal, 3.8?
Yeah. Let's see if I can convert that to decimal. Because technically your answer is more correct. 31 over 85 is the better way to write 0.38 some other digits.
What did you get, Sheriff?
I didn't even figure it out.
No, that's what you're supposed to do, because like for one wavelength it's the 286.
We'll have to look
Divide
up...
that by 4.
Yeah, I'll have to look up a manual for yours.
Yeah?
To convert it so it does the decimal points as opposed to a fraction. But it's pretty cool that yours does a fraction at the end.
Yeah,
I like that.
I was scratching my head there for a minute.
Yeah. So technically that is correct. And if you divided 31 by 85, it would probably give you 38 point something.
So can I use the fraction on the exam?
Unfortunately not. You have to pick one of the ones that they give, and they're all with decimal points.
Oh shit.
Yeah. But I will definitely work on it afterwards to try to make sure you can get decimal points from that, though.
Okay.
So, alrighty, moving on. What do we get? Same question, essentially, with different numbers. So if you made a half wavelength vertical antenna for 223 megahertz, how long would it be? So because we're over 30 megahertz, we need to use the 300, and we're doing a half, so we get 150. We take 150 and divide it by 223 gets us...
So where'd you get the 150 from?
because we need to take 300. So we have 300 as the base because we're over 30 megahertz, right? We have 223 megahertz. So we take 300 as opposed to 286. But then we're doing a half wave length as opposed to a full wavelength, so we need to take half of 300.
Oh, I'm lost.
Okay.
No problem. I'll figure it out at home. I'll read the book.
Okay. Yeah. So I guess if we could continue on. 64 centimeters. So if we move on again, we get... Yeah.
Yeah.
Okay, yeah. So to do it long form, we take 300, we divide it by 2, gets us 150. We divide 150 by 223,
Yeah.
gets us 0.673. But Industry Canada doesn't make a distinction between the 30 megahertz 300 and below 30 megahertz 286, so we need half of 286, gets us 143. So again, they're always doing that odd number as opposed to the 300. But if you do the calculation, you shouldn't have an issue because all of the answers will line up correctly. So if we go back, we don't get 67 anywhere, we get 64, which is close enough that we could consider it.
One, yeah.
So, alrighty. And oh, just to be funny, of course, they've included the 128 if you did a full wavelength. So always be careful that you're paying attention to what wavelength they're looking for. Alrighty, moving on.